Yeah, many thanks to the organizing committee for asking me to speak on behalf of the Lunar-VISE team and tell you about our exciting investigation of the Gruithuisen domes. So Maria really set me up well. She already kind of gave you an overview of Lunar-VISE, but Lunar-VISE is the Lunar Vulcan Imaging and Spectroscopy Explorer that was selected as a PRISM payload suite as part of the NASA's second call, and it was specifically chosen to land at the Gruithuisen domes. Our 10 Earth Day surface investigation is to really understand the formation of those highly silicic domes. And we are one of the payloads that is part of the CP21 payload or mission that's going to go no later than January 2027. So our rover and lander payload instrument suite is really designed specifically to address overarching science and exploration goals, including first, we really want to understand how lunar silicic volcanism works. And so we're going to understand that by first looking at the Gruithuisen domes and then applying that to the other silicic regions across the lunar surface. And then we also have an exploration goal of really trying to understand the geotechnical properties of the lunar regolith at this special location on the lunar surface. As I mentioned, our payload is a combination of instruments on a lander as well as a rover. On the lander, we have a suite of cameras. We have a descent camera that will be imaging the lunar surface as we're descending to the surface, and this will allow us to map our landing area as well as characterize how much of that landing area is disturbed by the interaction with the lander. And then we will also have a context camera that will be on the lander imaging the surface, building up a geologic map of our landing area, as well as watching the rover as it moves about and really understanding how the rover is interacting with the regolith. And both of these cameras are being built by Ball Aerospace and are based on heritage cameras. On the rover, we have a suite of spectrometers. Two of the spectrometers are being built by Ball. We have a visible and near-infrared imaging camera that will be used to map variations in composition and morphologies at high spatial resolution. This camera is similar to our context camera, except that we'll have filters on the camera that will allow us to have multispectral capabilities. We also have a heritage instrument in the LV Cirrus, which is based on L Cirrus, which is going to the south pole of the moon as part of CP22. Using the thermal infrared, we'll be able to get multispectral data, which again will help us understand the composition at really high spatial resolution. And then finally, but not least, last but not least, is the gamma ray and neutron spectrometer. This gamma ray and neutron spectrometer is going to be used to measure major elemental abundances as well as thorium. And this is an instrument based on Arizona State University's Mini-NS that's on LunaMap. Here's just an image. Obviously, as Maria mentioned, we don't have a lander or a rover yet. And so this is a very simplistic drawing, just kind of showing how the instruments are going to work on the rover. And so you can see here that our visible and near infrared, as well as our thermal infrared camera, are both bore-sighted, and they will sit in a single enclosure on top of the rover. Based on our height, if we assume that we're a meter off the surface, we should be able to see 3.6 meters in front of us. And at that distance, we'll have a resolution sub-centimeter. And then if you look here at the table, you can see that out to 100 meters in front of the rover, we should still be seeing on the order of tens of centimeters. So really great spatial resolution. Both of these instruments, they are bore aligned and they also rotate. And so essentially we'll get a 180-degree panoramic view of whichever direction we're pointing in, and we'll essentially be building up spectral maps as that instrument rotates through. And then on the rear of the rover and located towards the bottom of the rover is our gamma ray neutron spectrometer. And this is really to limit how much materials is between it and the lunar surface. So as I mentioned, our ultimate goal is really to understand the formation of the domes. And so to do that, we have multiple science objectives. And the first is really to map any local variations in composition. And we're going to do that in two independent ways. And so we'll be getting silicate composition from measuring the Christensen feature that Rachel just talked about, and Ben Greenhagen also gave a talk earlier today about. And so by measuring the position of the CF feature, which you can see on the y-axis here, this will give us a really good constraint on the silicate composition. And then we'll also be getting silicate composition from our gamma ray and neutron spectrometer. And so having these two different methods for measuring silicate composition will give us a really robust determination of the rock composition, which will really help us test those hypotheses for how the dome's formed. In addition, we'll also be getting thorium, which will also be really critical in understanding and constraining the formation mechanisms. Of course, what we really want to do is we want to take those compositions and put them in geologic context for where we're measuring these compositions across the dome. That's really key. And so not only will we be mapping composition, but we'll also be looking at rock and regolith properties, including the regolith thermal inertia and porosity. We'll also be correlating compositions with surface features and dome morphologies. And so this will be really critical in our understanding of how these domes formed. And when I say we want to study rocks and regolith, we are really studying rocks and regolith. So the intention is to be driving to these boulders and getting measurements at high spatial resolution along with the regolith. As I mentioned, we want to take what we learn here at the Gruithuisen domes and apply that to the rest of the silicic locations on the lunar surface. And so to do that, we have to be able to ground truth our observations at the domes so that we can then apply them elsewhere. And so to do this, we've chosen, and we've been very specific about all of our spectral channels on our instruments. And so for the visible near infrared, we've chosen channels that overlap with Clementine, Kaguya, and El Rock WAC. And for the thermal infrared, we've chosen channels that overlap with Diviner, Osiris, as well as Lunar Trailblazer. And so that will really make that critical link between our in situ surface measurements and the orbital data that will be collected. And then finally, we will be using all of our camera systems to really be looking at how both the lander and the rover are interacting with the surface so that we can get some really nice high resolution images and movies to be able to understand the geotechnical properties as we traverse around the dome. Most recently, we've been looking at picking a landing site. We've mostly focused on a location on the Gamma Dome, which is here on the left. And specifically, we've been looking at this region near the edge of the dome, which you can see in this beautiful El Rock NAC image. And you can see that there's this kind of nice flat plateau right here, which is where we've been looking at our landing ellipse. And we've been using criteria like looking at slopes, the terrain ruggedness index, the amount of boulders and craters and the illumination, all to pick the best landing site possible. And then as Maria mentioned, we do also want to pick a landing site that will allow us to look at the mare below or surrounding the domes, and hopefully even depending upon where the Peregrine 1 lander lands, we might be able to get overlapping observations of their landing site. So here's just showing an example of the hazard analyses that we've been doing to really pick the best landing ellipse that minimizes high slopes, high TRI, as well as boulders and craters. And so this is our landing ellipse. And if we put that in the context of that small impact crater that I was showing earlier, here's that impact crater. These are the boulders that we're very interested in getting close to. Here is our landing ellipse. And so assuming that we land right in the center of that landing ellipse, all of the green areas is where the rover will have line of sight communications with the lander. And so we're now looking at what our waypoints are going to be within these areas to accomplish our science. And with that, I'll just say that we're really excited to be building this payload suite and getting to the domes to really understand what they're made out of. And I'll leave my summary slide here, and I thank